Okay, welcome to our next video. This one's over section 2.5, which is about optimization. And this video is going to be different in a couple of ways. First off, you'll notice there's already a bunch of stuff written down. I actually went through this whole video and then realized that I never turned my mic on. And so instead of me redoing everything, I'm going to use my same notes that I wrote out for that video. And instead of writing it out, I'm just going to slowly reveal stuff as I talk about it. But the second thing is optimization is simply finding local extrema for an applied situation, which means we already know the concept behind it. We already know how to find local extrema because we cover that in 2.1. So I'm not going to split this up into two different videos and have a concept video and an examples video. I'm going to go through the concept really quickly, and then we're going to focus a lot on the examples. Because with these applied situations, this is really going to test our problem-solving skills, and each example brings something new to the table. And so, once again, we're going to focus on examples in this video. But let's talk about the concept behind optimization. Once again, optimization is really just finding local extrema. Why? Because if I want to optimize the area for a plot of land, what am I doing? I'm just finding the maximum area. If I want to optimize costs, I'm really just trying to find the minimum of those costs. So optimization is really just maximizing or minimizing. And so let's just review what we learned back in section 2.1. To find local extrema, I'm finding the critical points. How do I find critical points? Well, I guess what are critical points? That's what this is over here. This is a little reminder. It's where the derivative is 0 or it's undefined. And then how do we find critical points again? Well, we take the derivative of our equation and we set that derivative equal to 0 and then solve. Now you'll notice I kind of put in this extra step of create an equation. Back in 2.1, those equations were always given to us, but this process really hinges on having an equation to work with. And in some of these optimization problems and some of these applied scenarios, we're not given an equation and we have to come up with that equation. So once again, that's why we're going to focus on these examples to kind of see how that looks. But to help you out, I did come up with kind of some general steps that you can kind of look at to help you work through these optimization problems. First of all, since so much of this is problem solving and making sense of situations, step 0 can just be drawing a picture or a diagram to help you out. Sometimes that can be really, really helpful. Then our first step, step number 1, if I'm trying to optimize a value, I need an equation for that value. Why do I need an equation? In order to be able to take a derivative. So the first step here is I want to write the equation for the value that I want optimized. One thing that might help you in this is defining your variables. Remember, the dependent variables is whatever value you're optimizing. We really want to define what my independent variables are. Well, why did I say variables plural? Well, sometimes when we write this equation, we might have multiple variables that we're working with. And it requires the second step where I'm going to find and organize any additional information that's given to me so that I can put my step 1 equation, I can put this equation that I just came up with in terms of only one variable. And we're going to see an example, a couple of examples like this where this is going to be necessary. What do I mean by organize this additional information? I really mean create an equation for that information. So once I'm able to use this additional info to rewrite my step 1 equation in only one variable, we're then ready to solve for those critical points. Because once I have it in terms of only one variable, I can then go through these steps of taking the derivative, setting it equal to 0, and solving. Okay, so there's my kind of general process. And this may not make much sense now, but let's go through some examples so that it can make a little bit more sense. So let's start with number 6 from your homework. I guess I should preface this by saying, you're welcome. Feel free to go ahead and try a few of the problems out on your own. Problems 1, 2, and 3 are really straightforward if you want to try those, but it still requires all 3 of these steps. So you're welcome to try those out. And then as you get stuck, come back to this video and look at some of these examples that I go through. So let's start with number 6. So number 6 says, find the maximum profit and the number of units that must be produced and sold in order to yield the maximum profit. And then it gives me my revenue equation and cost equation. So step 0, draw a picture or diagram. This is a finance example. There's not much I can draw to help me make sense of this. So I'm going to skip step 1 and just move on to skip step 0 and just move on to step 1. What am I trying to optimize? I am trying to optimize profit. That means that I need an equation for profit. Well, neither of these equations are profit equations. So where am I going to come up with my profit equation? Well, we know that profit is just revenue minus cost. So therefore, we can come up with my profit equation by just doing my revenue equation minus my cost equation, which is just this 9x minus 2x squared minus x cubed minus 3x squared plus 3x plus 1. Notice I have parentheses. Those parentheses are important because you're minusing this whole function, which means I'll need to distribute that negative when I simplify. Okay, so now I have an equation for the value that I want to optimize. I have an equation for my profit. But notice how many variables am I working with here? Of course, I'm my dependent variable, but I only have one independent variable. Is there any additional information that it gives me? No, not really. So in this case, step 2 is not really necessary. I went ahead and simplified the equation for step 2, which is awesome. And I got negative x cubed plus x squared plus 6x minus 1. I have my profit equation. It's simplified. It's only in terms of one variable. I'm ready to solve for the critical points. How? I take the derivative and set it equal to 0. And I get negative 3x squared plus 2x plus 6 is equal to 0. How do I solve something like that? I have a quadratic function that I'm trying to find the roots of, right? It's set equal to 0. I'm trying to find the roots. Well, I could try and factor it, but this one does not factor nicely, so you need the quadratic formula. We went through the quadratic formula in one of the previous videos, so I'm not going to go through it again. But there's my a, b, and c. I put that into my quadratic formula over here, simplify, and I got 2 answers. I should be getting 2 answers, right? Because of the plus minus. I highlighted it, but I'll circle it again. I should be getting 2 answers. But you'll notice I've already crossed one out. Why can I cross out negative 1.1196? Well, because it's negative. What does x represent again? X is the number of units that you're producing. I don't want to produce negative units. So I can go ahead and cancel that one out, which is leaving me with just one answer, 1.7863. And that represents the number of units I'm going to produce. If I want to find the maximum profit, what do I do with that? I plug that back into my profit equation. Now, something to be careful here is when we're actually answering it, when we're actually plugging our answer into Pearson, it says round to the nearest whole number. Please remember that both of these terms are in terms of thousands, so thousands of dollars and thousands of units. That means when I plug this value in, I'm actually going to plug it in as 1,786 units. Don't round the 1.7 up to 2. Convert it in terms of thousands first and then round. Same thing with the dollars amount. Okay, but that takes care of number 6. So that one, there wasn't much to step number 2. So let's look at a different example where there's going to be additional information that we have to work with. Let's look at number 4. So find the dimensions of the open rectangular box of maximum volume. Why is this optimization? Because we're trying to maximize the volume. That can be made from a sheet of cardboard 25 inches by 14 inches. And you'll notice this one, you can draw a picture for step 0. So I've got my diagram by cutting congruent squares from the corners and then folding up the sides. So first thing you have to do with this problem is be able to visualize what's actually going on. I'm cutting out those corners and then folding along the dotted lines in order to make a box. Okay, so now that we have that in our minds, now that we've made sense of that, let's start working through my 3 steps. First, I need to come up with an equation for what? For volume. That's what I'm maximizing. So I need an equation for volume. Well, a volume of a rectangular box, that's a really simple formula to come up with. It's just length times width times height. The problem with that is that's 3 different variables. Length, width, height. How am I supposed to take a derivative if I've got 3 different variables that I'm working with? So that's why we're going to need step 2. What additional information does it give me? Well, it does give me the length of the cardboard sheet and the width of the cardboard sheet. So do I just plug those in for width and length? Are those fixed values? If I keep my length as 25 and I keep my width as 14, then what size rectangle can actually cut out of the corners? I can't actually cut any corners out if I'm keeping that whole length and keeping that whole width, which means my height's going to be 0, and therefore my volume's going to be 0. That's not going to give me a maximum volume. So I don't want to plug those numbers in straight. What other information does this give me? It tells me that the squares that I'm cutting from the corners are all the same. That means if I say that this length is x, I'm choosing x because we don't know what size squares we're cutting out. Then what's this distance right here? Also x. What about this distance? It's also x because it's squares. All of these distances are a length of x. So this is me introducing a new variable here, x, that represents the size of the square. So now can we relate length, width, and height to that value x? Let's start with height. Once I fold up those sides, once I cut out the square and fold up the sides, how tall are those sides? They're going to be as tall as whatever I cut out of the corner. So it turns out my height is just x. Well, what about my width? I know this whole length is 14, but what about this length? Well, to get that length, I'm just taking away, I'm cutting out 2 squares from either side. So that length right here is just 14 minus 2 x's. And I can do something very similar to my length. I'm just taking off 2 squares from each side, and so my length ends up being just 25 minus 2x, because it's that full length, but taking away 2 squares from either side. So now I have a volume equation that's 25 minus 2x times 14 minus 2x times x, because I've converted each of those length, width, and height values in terms of this new variable x, representing the size of the square that I'm cutting out. Multiply all those things together, and you get this 350x minus 78x squared plus 4x cubed. I now have my volume equation in terms of just one variable x. And therefore, I'm ready to go ahead and find my critical points. I'm ready to take the derivative of my function in terms of x and set it equal to 0. So I get 350 minus 156x plus 12x squared. Notice I have a, b, and c down there because guess what I have to do again? I have to use the quadratic formula. So that's what all of this work is. Plug it into my calculator and I get 2 answers again. And once again, I've crossed one out. But this one's not as obvious of why. Let me erase this and show you what the answer was. And we can talk about why I canceled that, I crossed that one out. What does x represent again? X represents the side lengths of the square that I'm cutting out. If I come up here and cut out squares that have a side length of 10.1, well, that's more than half of my width. That's me cutting out a square that's this size. And then if I do it on the other side, my squares end up overlapping. It ends up giving me a negative width. So that's why this one does not work. And I have to just stick with that other length. So the length I'll be cutting out is 2.883. Now the question is actually asking for the dimensions, so the length, width, and height. Now that I know my x value, I can just plug this in for x in this problem. And that'll also help me find the volume. But perfect, this is a great example of one where drawing a picture helped. Your initial formula was in terms of lots of variables, but I used my additional information to put it all in terms of one variable so that I could take the derivative and set it equal to 0. Last example, Pearson saved the best for last, and so did I. This one's a fun one. So in this one, we have a retail outlet that sells calculator, and on average, they sell 600 calculators per year. So they want to make sure and have 600 calculators available to sell each year. But it costs $2 to store one calculator for a year, and it costs them to reorder calculators. There's a fixed cost of $6 every time they reorder, plus the $2.35 to ship each of those calculators. How many times per year should the store order calculators, and in what lot size, in order to minimize inventory costs? Why is this optimization? Because we're minimizing a value. We're minimizing inventory costs. So before I reveal this equation, let's talk about it a little bit first. Or I guess first of all, you'll notice there's nothing for step 0. Once again, there's not much I can do to draw a diagram here. So let's just think about what my equation is going to be. Inventory costs. That's what I want to write an equation for, because that's what I'm trying to minimize. But what all constitutes inventory cost? Well, there's really 2 different pieces. First off, it costs money to store calculators. And second, it costs money to reorder the calculators. So there's 2 pieces to this inventory cost. And so let's look at each of these pieces. Storage costs, it's $2 per calculator. And for now, I'm going to introduce a variable here, and S is going to represent the number of calculators we're storing. Now let's think about this. If you're storing calculators, but people are buying them consistently, it's hard to always be storing the same amount of calculators. That number is going to be constantly changing as you sell calculators. So instead, I'm going to add something to this definition. This is actually going to represent the average number of calculators being stored, because that's how we're going to actually put it into a mathematical equation. Instead of it represent a specific number, it just represents on average how many calculators are we actually storing. And so that's what S is going to represent. Now let's move over to reorder costs. Reorder cost, it cost me $6 plus $2.35 for each calculator I order. So in this case, you'll notice I introduced another variable. X represents number of calculators ordered. Well, that's what this lot size is talking about. That's exactly what lot size is. Lot size is the number of calculators you're ordering. So it's $6 plus $2.35 per calculator I order. And then I'm not just doing that once. I might be doing that multiple times during a year. So I'm going to multiply that by n. I'm going to erase this because we are going to talk about that in just a little bit. So here I have my inventory cost equation that's got 3 different variables in it. So now I need to make sense of each of these variables in order to try and get this all in terms of one variable. Let's start with the number of reorders. What info have we still not used? What additional piece of information have we not used in this equation? Well, I still haven't used this 600 piece. So let's look about some hypotheticals. What if we really want to minimize our reorder costs by only reordering once? Let's just order calculators once per year and call it good. That means X is going to be 600. What would N be? If I'm ordering all of my calculators at one time, how many times do I have to order per year? Only once. Now, this may not be the smartest idea, because if I do that, what happens to my storage costs? My storage costs get really, really high because you're storing lots of calculators. So let's lower that number. What if I let X be 100? What if I only order 100 calculators at a time? How many times do I have to reorder? Well, if I need a total of 600 calculators by the end of the year, I need to reorder 6 times. So it turns out there's this inverse relationship between the total number of calculators and the number that I reorder, and it's as simple as 600 over X. And you can think of some other situations to check that if you want, but that's what N ends up equaling. So that takes care of N. That will let me get N in terms of X. Now let's think about S. Remember, S doesn't represent the number of calculators I'm ordering. It represents the average number of calculators that are being stored. So let's think about calculating that value. What's the maximum number of calculators that I can store? Well, the maximum number is right after I just reordered. If I reorder 100 calculators, then I'm going to immediately put those calculators into my storage, and that's the maximum numbers I'll have being stored in there at one time. Why is the maximum? Because we're assuming that we're not going to reorder until we've sold out of calculators, meaning that my minimum amount is 0. The minimum amount I could be storing is 0 calculators because that means I've sold out and I'm ready to reorder again. So if I average those two values, I get x over 2, and that represents my S value. So I was able to take this additional info in order to organize it into equations that I can then plug into my inventory cost equation to get this. 2 times what is S? S is just x over 2, plus 6 plus 2.35x times n. What is n? N is just 600 over x. And now that equation is completely in terms of x, and I can simplify it. So simplify it, I get x plus 3,600 over x plus 1410. 1410 is $2.35 times 600, and the x's cancel out because one is in the numerator and the other is in the denominator. Now that that's all in terms of one variable, I can take the derivative, and I get 1 minus 3,600 over x squared. Why? Because, remember, I can rewrite that as 3,600 times x to the negative 1, use the power rule. When I set that equals 0, notice I do have an x value that makes this undefined. If I let x equal 0, I get an undefined value. But I've already crossed that out. Why am I ignoring this case? Well, what does x represent again? X represents the amount of calculators I'm going to order. Does it make sense for the company to order 0 calculators each time? Absolutely not, because then the number of times you reorder ends up being an infinite number of times, and we run into all sorts of problems. So we can ignore that answer, and we can keep going. So as I continue to solve for this, I can get the 3,600 over x squared to the other side, multiply by x squared, square root everything, and I get x is equal to 60. Much more reasonable answer. That means each time I reorder, I'm ordering 60 calculators. That means what is n going to be? 10. That means you're reordering 10 times. What's the average number of calculators you're storing? I can find that too. That means on average, I'm storing 30 calculators. So that's the trickiest one on your homework. Hopefully the other ones you'll be able to get on your own. But if you have any issues as you're working through the homework, please reach out. Please talk to me. I'd be happy to help. Good luck with the rest of the problems, and I'll see you in the next video.